Everybody, welcome to Chapter 3. Chapter 3 is all about quadratics, and we're going to be taking a look in Section 3.1. It's kind of got a couple of pieces to it, so it's going to take us for a few days that we're going to be able to solve quadratic equations algebraically. And as we take a look through this particular chapter, again, a quadratic equation, remember when we were doing our roller coaster project, is where, again, we're going to have y equals ax squared plus bx plus c. And again, the graph is a parabola. And it has answers, it has roots. And so that's what we're going to be focusing on and being able to find those roots. And so there's three ways that we can find these roots. One we can focus on is we can graph. And we'll come back to a little bit of graphing again this chapter, but you'll find that this chapter doesn't have as much graphing. And then we get into using square roots. So by being able to take the square root of each side. Or we might have to do some factoring. If we're going to do some factoring, we're going to have to get the equation to equal 0 and then factor and solve. And then our next strategies will be complete the square and then the quadratic formula. And so these are the things that we're going to be talking about in this particular chapter. But for 3.1, our focus is going to be factoring and again be able to solve it algebraically. And so in order to do that, we need to be able to simplify a radical. And so hopefully you remember this from good old should say Algebra 1. And remember some of this. You also would have saw some of this in geometry. So there's a couple ways to think about this one. One way it is taught is like if I want to simplify the square root of 63, I don't want it to be where you're giving me the decimal answer. We want to reduce this as a radical. So one way to do this is to get the prime factorization of 63. Remember, a number that's prime is divisible by 1 and itself. So therefore, I know that 9 times 7 is going to make 63. 9 is not prime, so I can break 9 into 2 3s. So therefore, and then we look for pairs. So I have a pair of 3s. And then this is where we would talk about they're escaping from the jail that they're in. This radical is a jail. And so one dies in the attempt and the other one gets out. And so my answer is 3 root 7. Some other teachers teach it this way. They want you to find the highest perfect square that goes in. So 1, 4, 9, 16, 25, 36, and so forth. And find the highest number of that goes into 63. So that would be also 9 times 7. 9's the perfect square. So since that number's perfect, they did their chores, they did everything they needed to do, they get out of the house. So the square root of 9 is 3. And since the 7 isn't perfect, therefore it's going to stay in the house. It didn't do what it needs to do. And again, I'm going to get 3 root 7. So again, I don't care which way you do it, just as long as you get 3 root 7. So that's the important way of doing it. For the next one, for 32, we could break it down into the primes, which is 2 times 2 times 2 times 2. There's 5 2s. And then when we look for pairs, we have 2 pairs. One again dies in each attempt. So we're going to multiply this 2 times this 2, because they're both going to come out, which is going to make 4. And then I have 1 2 left in the radical, so it's 4 root 2 for my answer. Or if I did it the other way, the highest perfect square that goes into 32 is 16. So it'd be 16 times 2. The square root of 16 is perfect. He comes out. They did all their chores. The 2 is not perfect. It stays inside. 4 root 2. Finally, for number 3, same idea. 20 is really, if you do it the second way, 4 times 5. 4 is the perfect square. So again, he comes out. He gets square rooted. And then the 5 is not perfect, so it stays in. Or again, we can do the prime factorization. See that again, we have a pair of 2s. 1 dies in the attempt. The 2 comes out, 2 root 5. So hopefully you remember a little bit about reducing some of these radicals from the past. Now, we're going to go on to solving equations and go back to the page that I just kind of skipped over. So for number 4, what you're going to do is to solve something, we're going to square root each side. So if the square term is by itself, you're going to want to square root that. So when we do that, we'll get t equals. Please remember that there's 2 roots. So you'll always have a positive root and a negative root because you're going to always have 2 solutions because it's quadratic. And then we square root the 400, which would be 20. And there's my answer. So t is equal to plus or minus the square root of 20. The next one, now the x squared is not by itself, so we're going to have to get it isolated. So we're going to have to subtract 14 both sides and get 56. And then we're going to divide by 2 because we need to get that 2 out of there. And so that would give me 28. And this is where we needed that skill from the last page with the solving of the radicals. Because when we square root this does not come out nice. But I don't want you to tell me that the answer is 5 point whatever. I want you to reduce it as a radical. So depending on how you want to do that, this is really 2 times 7. So I have a pair of 2's. So therefore, x would equal 2 times the square root of 7. And again, we need a positive root and a negative root. Finally, for the next one, solving algebraically, we're going to add 19 because, again, we're going to isolate. Now, this term is already squared and it's grouped together, so don't ungroup it. So we want to get rid of that squared. So now is the perfect time to square root it. So we're going to get 2k plus 3 equals plus or minus 10. So that really, in essence, though, gives us two equations. So either 2k plus 3 equals 10, or 2k minus 3 equals negative 10, pardon me, plus 3 equals negative 10. And then we solve those two equations. So this one we'd subtract 3, and then divide by 2, so we'll get 7 over 2. This is set notation, by the way. And then subtract 3. So we'd have 2k equals negative 13, divide by 2, so we would end up with negative 13 halves. So that's kind of a quick, again, if I have only one variable that's squared with no other variable there, you can solve these things pretty algebraically very nice. Now, what happens if it's not the only variable? So like maybe there's an x squared and an x. Well, then we need to do factoring. So now I'm going to go back to the page I skipped. So some great tips for factoring. So basically Mrs. Cable's guide to factoring, as you will. First thing I always look for is the greatest common factor, because if there's a greatest common factor, that's the best thing to do. You just take that out. Second, look for perfect squares, the numbers that we just talked about, because those factor super duper nice. If you have a number in the a position, the ax squared piece, where a is 1, then you know what we could do? We can just do the product sum game. So like what two numbers multiply to this and add to this. If the number in the a position in front of the x squared, then we might have to do something like a guess and check. And so I didn't put that in here, but that's definitely something that we'll get to in our notes. If nothing works, it could possibly be prime, or we'll find out later on it might just not be factorable, so we might need to do a different strategy. And then try again and recheck, you know, if all else fails. So this is where the big part of the lesson where we need to practice and hone, because some students really struggle with their factoring, which is coming back from Algebra 1. And we don't do a lot of factoring in geometry. So it's been a while since you've seen some of this stuff. So looking at the zero product property, if you would imagine two numbers that would multiply to make 0, you know something about one of your numbers. And so hopefully you realize that one of them would have to be 0. Okay, so when we solve by factoring, we know things are factored when we see parentheses. So in number 7, this is already factored. So this is easy. So according to the zero property, either x plus 3 equals 0 or x minus 2 equals 0. And then we solve. So this one we'd subtract 3. So x would be negative 3. This one we'd add 2 each side. There's my answer. So either x is equal to negative 3 or x is equal to 2. See how nice it is when it's already factored. So if something's factored, don't unfactor it. Next piece. This one in number 8, hopefully you notice they have something in common. A lot of times when you have two terms, very often do they have something in common. So in number 8 and number 9, these are what we call the GCF problems. So we're going to take out an x. So if I have x squared and I divide out the x, there'll be 1x left. And then 5x, divide that by the x, we'll have 5. And then that's going to equal 0. So x is going to equal, so this plain old x here is going to be 0, or x minus 5 is going to equal 0. And so then we have our two solutions, 0 and 5. Number 9's the same way. Again, they also have an x in common, which I'm going to divide out. So 7x squared divided by x is 7x. 2x divided by x is 2. And it equals 0. Now, one thing I wanted to kind of mention to you also is that you can always distribute this back out to make sure that it makes the original problem. Because if I do x times 7x, you will get 7x squared, and x times 2, you'll get 2x. So that's a quick way to check to see if you're factoring it completely. So this single x will equal 0, or 7x plus 2 would equal 0. And then we're going to solve this. We're going to subtract 2. Divide by 7, so we're going to get 0 or negative 2 sevenths. All right, so those are GCF. The biggest thing with, again, when we're solving, make sure that your equations are equaling 0. So hopefully you're noticing that in number 7 and number 8 and number 9, all of them equal 0. Now, for number 10, we don't have a GCF. It's a trinomial. And so next thing we would check for is see if 28 is a perfect square. But it's not. So therefore, what we would do with this particular one is we get to play what I call the number game. So this is going to be my product. This is going to be my sum. So we're trying to think, again, each one gets an x because we have to divide it evenly. And so we think what two numbers multiply to negative 28 and add to negative 3. So that's when you start really needing to know your multiplication tables. So for me, I know that that's 7 and 4. And because it's got to multiply to a negative 28, the signs are going to have to be plus and minus. And in order for this to work and add to negative 3, I know the 7's got to be minus and the 4's got to be plus. Because negative 7 times 4 is negative 28, and negative 7 plus 4 is negative 3. Now we use the zero product property and set them equal to 0 and solve. So we would get 7 and negative 4. And we're done. Number 11 is very similar, except it doesn't equal 0. So again, you need to make one side equal 0. So I'm going to add the 36 and get that on the other side. And 36 is a perfect square, but on perfect squares, you can also play the number game. So this one, you're playing what two numbers multiply to make 36 and add to negative 12. And so by doing that, we're going to have x minus 6 and x minus 6, because negative 6 times negative 6 makes 36, and negative 6 plus negative 6 makes negative 12. Notice this is the same parenthesis, so you really don't need to solve it twice, because that's kind of a silly thing to do. So therefore, I'm going to get just one double answer, which we call a double root. And so my answer will be 6. 12, I'm going to skip for a minute and come back, because that's actually a little bit harder form of factoring. So I want to take a look a little bit at 13 and 14. Now 13, again, it doesn't equal 0. So I'm going to subtract 3x both sides, so it does. 5x minus 3x is 2x. And then that is going to equal, or probably negative 35, and then equal 0. And again, we're going to go to the number game because there is a 1 in front of that x squared. So we're going to think what two numbers multiply to negative 35 and add to 2. Now, again, because it's multiplying to a negative, I know I need a plus and a minus. And the most common numbers that multiply to 35 would be 7 and 5. Now, if one's plus and one's minus, but it needs to add to 2, that tells me that the plus must go with the 7 and the minus must go with the 5, because 7 times negative 5 is negative 35, and 7 plus negative 5 makes 2. Then from there, again, set each parenthesis equal to 0 using the 0 property and solve. And so we would get negative 7 and positive 5. 14, very similar. Again, get that one side to equal 0, so add 15. And again, since there's a 1 in front of here, play the number game. Each one gets an x again. So we got to think what two numbers multiply to positive 15 and add to 8. And so that would end up giving me 3 and 5. Because 3 times 5 is 15, and 3 plus 5 is 8. And then set your equations equal and solve them. So we would get negative 3 and negative 5. So that's done. Okay. All right, for the last two, 16, by the way, I'm not going to finish on this particular podcast. And the reason why is this is not factorable. You can try it out and figure out why that is true. It is solvable, but it cannot be factored. So we'll have to do something else. We'll either have to do something called complete the square, or you would have to do the quadratic. Personally, I think the quadratic formula would be the best approach to go with that one. So we got two more to talk about. So how do I solve it when there's a number in front of the x squared that's a number other than 1? Well, then you get to do the fun guess and check kind of factoring. So first of all, I got to move the 10 because I got to make it equal 0. This is the kind of factoring that gets students not happy because they don't like these. Because you have to guess and check. And you check your out term and your in term, and we get that from FOIL. Remember, first, outside, inside, last. So for here, I need numbers to multiply to the front. So I worry about the engine and the caboose of the train. So I need numbers that multiply to 3. So I'm going to have 3x and 1x. And then I'm going to need numbers that multiply to make negative 10. So let's see. I'm going to have, let's try a negative 5 and positive 2. Now by doing this, I have to check my out term and my in term to see if the negative 13 was created. So negative 5 times x is negative 5x. Then 3 times 2 is 6x. Uh-oh. 6x plus negative 5x isn't 13x or negative 13x. So, what should we do? We guessed wrong. Well, the first thing I would do is I'd go back and change the numbers around. So what if instead I have a minus 5 here, and let's put a plus 2 there and see what happens and check. So when we check, here's going to be 2x. Now I'm going to check this. I'm going to get negative 15x. Look at, if I add these, I get negative 13x, which means this is the right factoring. So now I can actually solve it. So 3x plus 2 equals 0. X minus 5 equals 0. So this one, the second equation is easy. That's just 5. This one, we're going to minus 2 and then divide by 3. So we'd get negative 2/3. So that's the hardest part of ones that can be factored. And that also relates to number 15. For number 15, you would do the same thing. We'd subtract 5. So we'd have a negative 12. And again, try to work with numbers that multiply to 3. We're going to look at the engines, so 3x and 1x. This time, though, we're thinking of numbers that multiply to 12. So part of me is thinking negative 4 and positive 3, but I don't know if 16 is going to be accomplished with that. So we would double check that. So let's see, I'll get 9x here, negative 4x here. Ooh, that didn't work. And I really don't know if I think I want to switch the numbers around because in the beginning, see how we have 3, 16, and 12? They're not divisible by the same number. So I don't want to put the same number in with itself because then that means it has a GCF. So maybe 4 and 3 are not the right multiple to use. So we can change numbers too. So let's see. What if we tried 6 and 2? So we'll make this be a plus 2. And that's still my 1x, and let's make this a minus 6. And then let's check it. And so for this one, I'm going to have 2x in the middle, and outside I'm going to have negative 18x. Ooh, that makes negative 16x. I got it. So then the next thing we would do is then, again, now that I have the factoring correct, set the equations equal to 0. And solve. The second equation, again, is easy. That's going to be 6. And then the first equation, you're going to subtract 2 and then divide by 3, and we'll get negative 2/3. And that kind of concludes this whole factoring, solving quadratic session. And again, you got to really practice that factoring. That's really super important. So hopefully you enjoyed the podcast. And as always, have a great day.